Hello everyone, welcome to today's video. So we were doing last time. Okay, so yesterday was it? Yeah, I started off coordinate geometry, or as I called it, Euclidean space geometry, and so this is the path in which today's video is going to go. So for the first two-thirds of today's video, we'll be looking at angle between two lines. We're going to do some angle between two lines, and then towards the end of this video I'll talk about the mathematical basis, which is the abstract basis of Euclidean coordinate system. So I'll kind of contrast between Euclidean space geometry and what a coordinate system is, the definition, the mathematical definition, how mathematicians even invented. It's not a derivation, it's a feeling of what a coordinate system is and how we use it to define things, and why it's not just Euclidean space geometry, but we're not there yet. So when I get there, we'll talk about it. So first things first today. So today I'm going to start off with angles between two lines. Sorry, the angle singular between two lines. So what are the requisites? I'm just going to write the requisites. The requisites is something we've already done before. It's that you have to know this. Well, even if you've kind of already forgotten what it is, the identity of the difference of angles for the tan function is equal to and in my last playlist, in my last videos, I kind of show this derivation is going from sine A plus minus B divided by it's derived from the fact that sine tan A plus B is equal to sine A plus B divided by cosine A plus B. Then if we can find what tan A plus B is, we just reverse deductively show that wherever you have a minus sign, you change it with a positive sign, and that will be the case for minus. But that's not what we're doing today. So if you can keep this in your mind, this is heavily what the whole video today is going to be based on. Okay, now we start. So we have two lines, line 1 and line 2. And the angle between line 1 and the x-axis is alpha, while the angle between line 2 and the x-axis is beta. However, you can show that this angle between L1, that's line 1, and line 2 will be beta minus alpha. Let's call that something like that. I don't know how to write alpha properly, so let me just write it like this. Yeah. So the angle between that is some angle phi. I like using phi as an angle. So is equal to phi. Also, no, this is in 2 dimensions, but I'm ignoring the y-axis, so something like that. This is the y-axis. Okay. I want you to recall something. That in the last video, we showed, or I was able to, I hope I was able to convince you that this fact is true. That tan of theta equal to the slope of the line, where this angle theta is the angle between the line and the x-axis. Now, we know that this, let's just call this a fact. Okay, so whenever I put like what's it called? An ash sign, it means it's something you should note down. Okay, so this is from last video, right? So now I'm going to show you something about this later on. Just hold on to this. Let's explore this. The first one. So we know tan of phi is equal to tan of beta minus alpha. We could explicitly express tan beta minus alpha as this, but before we do that, I need you to note some other things down. That tan beta is equal to the slope of L1, and tan of alpha is equal to the slope of line 2. I think I got that the wrong way. Tan of alpha, I got that the wrong way. So it's meant to be tan beta, because beta is the angle between L2 and the x-axis. So we have okay. As I said before, hold on to this very tightly. I'm going to show you something about this. So we can further write down the expression for tan beta minus alpha, and that would be okay. So note that. So that's the case. But we've already expressed what tan beta, what tan alpha is. So we just have to kind of make everything more compact. So I have that tan phi, where phi is the angle between line 1 and line 2, is equal to okay, so that's the case. So I'm telling you that the angle between two lines is a function of their slopes. Listen carefully. The angle between two lines is a function of the slopes. It's more or less me telling you y is a function of x. That simply means the components that make up the function y are x's. So if you have, let's say a polynomial, let's say f of x equal to x to the fourth plus x to the third plus x to the second power plus x plus some constant, that's y. So y is a function of x. In this case, I say y is a function of this, the angle between two lines is a function of the slopes. And what is that function? Is the trigonometric function tan. So I say that this angle phi is equal to m2 minus m1, 1 plus m1 m2. Recall something though. Recall that tan of theta is equal to n for this kind of coordinate system. I said that tan of this angle is equal to the slope. Now, but if you think of this, obviously this is x and this is y. If you think of this, well, this is like the coordinate system that everyone knows about, where this case is true. Tan of the angle between the x-axis, I said axis like it's plural, it's axis, and the line is equal to the slope. So it works the same way that the angle between two lines, in this case, two lines is the x-axis and the line, which I've just drawn, is a function of its slope. Okay, so there's a difference. Here I said, therefore, this angle theta is a function of its slope. It's a function of the slope of the line. The angle between the x-axis, and the line is a function of its slope. So it's equal to tan inverse. But here I actually said something. Well, if you look at these two things, you have to agree with me that the x-axis is actually a line that goes infinitely forever. Let me show you the slope of the x-axis. I remember I said m is equal to delta x divided by delta y. Okay? Now I have to give you a feeling for what this is. Sorry, delta y divided by delta x, Jesus. Delta y divided by delta x. Now you see, obviously, for the x-axis, there is no change in y because y is constantly 0. So m is equal to 0 divided by some number. Let's say, because x goes to infinity, so let's just say it's infinite. But I hate writing things like this, like 0 and infinity in the same equation. It doesn't want to even make sense. Because, well, infinity is not a number, it's just an idea of something you can't ever reach. It's just impossible. So let's just express infinity as 1 divided by 0, right? So if I do that, you see that m equals 0, the slope is 0. Right, so that will be the equation of this line, which is the equation of the x-axis. But I hate writing infinity. So even if you restrict x to be the change in x should be some constant number, any 0 divided by any number will always give you 0. That's a mathematical fact. And this is equal to 0. Okay, so this is where I have to be careful because I've already defined the angle between two lines, and here I redefined it. Therefore, I can say that this is like, okay, there's something about math, especially in physics actually. It's a property of nature that if you mathematically find something and you are, kind of a bit ambitious about your formula, about your mathematics, and you find a more general case about your whatever you're looking for, whatever you're trying to find about nature. The thing is, if someone did some specific findings, mathematical findings, some years ago, and someone else, say 100 years later, does something else related to what the person who did the mathematical finding 100 years ago did, And the person who did it 100 years later tries to do the same thing, but in a more grand style for more general cases. The thing is, the larger formula, the larger equation always encloses the smaller one. That is, for special cases, you always see the smaller formula. A good example is Newton and Einstein. If you derive, well, not I know how to anyways, if you derive, I think I can give a brief example. If you derive Einstein's field equations, and for some specific cases, you get the fact that F equal ma. F equal ma is is as far as Newton was able to go, but that's a smaller formula. So Einstein's theory is a more general theory of it's a bigger formula than what Newton did, but that's not what we're looking at. Well, it's the same analogy here. So if I say that, because let's say this is, let the x-axis be line 1, so we know that's at tan phi is equal to m2 minus m1. I'm going to clean this soon, but this is what I'm trying to show you. If I say that let the x-axis be and this line be L is equal to L, you see that the angle between the x-axis, and so this is going to be, so the slope for the x-axis is 0. So the slope of the x-axis is equal to 0, and the slope of the line is equal to some number m. We don't know what it is, right? So I'd say the angle between both of them is equal to this ml minus m1, which is 0, divided by 1 plus m1 times 0, and that's equal to ml. M1 which is equal to m, which is the slope of the line. Okay, so that's that. It's just, I'm just trying to show this in a more grand scale, that this is true. Okay, so that's that for that. So what else can I do? Yeah, so another thing I want to mention is, so recall how I said this is true. Well, I didn't say that it's true. Mathematics told me to say that it's true, or nature did at least. That is true. So tan of the angle between the x-axis, so that's the slope equal to 0, and the line L is equal to is equal to the slope of the line L, right? So, but look at this. Can we call tan of phi? So I'm asking, is tan of phi equal to a slope? And well, perhaps surprisingly or unsurprisingly, the answer is yes. It is equal to a slope. But it's equal to a slope in a different coordinate system. And what's that different coordinate system? This was our original coordinate system that had L2 and L1. This angle here was phi. Let's disregard the other angles. But tan phi will be an angle. I guess I have to, because I need more space. This was the original drawing. Oh, sorry, the original coordinate system. L2, L1, phi. tan phi will be a slope. Sorry, tan phi will be a slope of the line L2 if the coordinate system has changed such that this is y prime, this is y, this is x, such that L1 is equal to our new x-axis, which is x prime, x prime. Okay, I'll show you some transformations here. Okay, so this is the case. Tan phi is equal to m2 if you're taking the slope, that'll be the slope of line 2 if you're taking L1 to be a new coordinate, to be a new what's it called? Is it directrix? Yeah, new directrix, because x prime is a new axis now, so it'll be a slope. Now let me show you some common coordinate system transformations. So if you have two coordinate systems where the angle differs by some variable theta, in this case, let's erase this line. Let's draw it again. So we have our normal coordinate system that we all know. Angle between the x and the y axis is 90 degrees, x, y. And we have another coordinate system, y prime and x prime, and they differ by some angle with an angle theta. Now we want to do some coordinate system transformations. That's the idea. The transformation is that we take x prime to be a vector, an infinite vector. Obviously it has to be an infinite vector because it just shows a direction, and it's off by the x-axis, that's what, by some angle theta. So we have that we treat x prime to be a vector, which it is equal to x cosine theta prime plus y sine theta j. Note how I put those little hats on those i's and j's. It's because the I and j are unit basis vectors. So I is defined, it's a unit vector as 1, 0, and j is defined as 0, 1. After complex, I think it's I'm not too sure if it's after complex numbers, I'll go fully into the depth of the unit basis vectors, and we can do some more vectors. But for this case, just know that this is true. So it's a unit vector. That's why I put a hat on it. And, well, what is y prime though? Is equal to something. I don't know what that is. But wait, let me see if I can figure that out. So from plane geometry, I just remembered something. Maybe I'll do plane geometry. It's like a whole thing on its own, plane geometry. From plane geometry, I know that this angle between the new x-axis, which is x prime, and the original y-axis is 90 minus theta. What is this angle though? Let's call this angle x. Maybe to some people it's obvious what the angle is. I'm not going to say what the angle is, but follow my line of reasoning. Normally, before this new coordinate system was rotated by the angle theta, they were both aligned, yeah? Now, if I tilted by some angle theta, in which the x prime is off by the x by some angle theta, it must logically follow that, obviously, if y is still held in the same position, it's tilted off the original y-axis. That's y prime is tilted off the original y-axis by the same angle theta. But how do I algebraically show this? I know the case that the angle between y prime and x prime should be 90 degrees. So the sum of this angle, that is x plus, is equal to 90, in which case x minus theta is equal to 0, in which case x equals to theta. So yeah, so that's a vector that's in the second quadrant, right? So I know what it is now. I know that y is equal to x cosine 90 plus theta I plus y sine 90 plus theta j hat. Cosine 90 plus theta is equal to minus sine theta, so I have y prime. So let me do it more, let me generalize it now. So this is the conclusion. X prime is equal to x cosine we're not too focused on this. This is not actually part of coordinate geometry, but this is kind of giving you, like, you know, a feeling of, yeah, why this is true. So this is the law of transformation, at least for this coordinate system that's off by some angle theta. So what does this tell you? It tells you that if you want to find the coordinates of some point in our new frame of reference, our new coordinate system, we have to, okay, this is what it tells us. Well, if we're treating them as vectors, which is what they are actually, but vectors gives you the intuition of direction, so you understand what's going on instead of just numbers. So it tells you that you pick the original x coordinate, multiply that by the cosine of the angle in which that the angle, you know what the angle is, the angle between the new coordinate system and the old coordinate system, and that'll give you the new so that'll give you a number here. Add that to this, that'll be the new x prime coordinates, the x coordinates for the new coordinate system. Do that for here as well, you get an answer. So that's the transformation law of coordinate systems to coordinate systems. Yeah, so that's about that. So what else? So this is kind of everything. Everything kind of follows. So if you want to say, let me just quickly do this for you. I'm not gonna waste time. So if the angle between two lines is 90 degrees, in which case they're perpendicular. So if I say L1 is perpendicular to L2, how do we show that? So it'll be that phi, this is supposed to be a tan inverse here, I hope you know. Phi is equal to tan inverse of this. So it will be that, so if this is this, therefore phi is equal to 90 degrees. No, pi over 2. Pi, get used to the fact that you use pi. So pi over 2, tan of pi over 2 is equal to infinite. And I already defined infinity to be 1 divided by 0. So I have 1 divided by 0 to be equal to M2 minus M1. Of course, multiply. We have that this equals 0, so of course multiply, I have 1 plus M1 M2 is equal to 0. If I have M1 M2 is equal to -1, M1 is equal to -1 divided by L2. So this tells us that if you have two lines that, two lines that are orthogonal to each other, or two vectors that are orthogonal to each other, we get that later. Two lines that are perpendicular to each other, the slope of one line will be the negative inverse or the negative reciprocal of the other one. It's that simple. So if you do for parallelism as well, so two vectors are parallel, it's either the angle between them is 0 degrees and 180. Tan of 0, that should be 0. So tan 0 is equal to 0, so I have M2. Is it 0? Yeah, it's 0. So if you cross multiply, this is 0 divided by 1, so you have M2 minus M1 is equal to 1, so M2 is equal to M1. I will further go into this later on and tell you that this signifies that two vectors are scalar multiples. If two vectors are scalar multiples, it means they're moving in the same direction or they're parallel to each other. They could be okay, so when I say they're parallel to each other, it simply means that they're either 180 degrees to each other or they're moving in the same direction at 0 degrees to each other. Yeah, so that's about that. So maybe next time I'll do some questions, I guess. 2 or 3 questions, then I comment the next video. So that's that. This is literally, we've already gotten to half of coordinate geometry. So what's the rest? I said that I would spend 2/3 of the time talking about what's relevant and 1/3 of the time talking about what's irrelevant. So it's time for the irrelevant stuff. Okay. So this is for the much more mathematically minded people. So what's a coordinate system actually? What's the Euclidean space, or the Euclidean Cartesian coordinate system? Okay, so what mathematicians have done for us, they've defined a way for us to use n dimensions of a coordinate system. Now, that probably makes no sense. Okay, so let me go, because I'm trying to think of it as I go. What is a coordinate system? A coordinate system is a mapping of things, right? Mapping of positions. But that's because I'm a really physicsy person, so I see this mapping of things. But coordinate systems are not just used for mapping things in space. It could be used to describe quantity over price in economics. It could be used to it's used in business. It's used in everything. Because I'm a really very physics inclined person, so I tend to keep on using the word space and so on and so forth. So I've been using the examples I've been doing are based on distances between two people and so on and so forth. It's not always the case, obviously, but I know that's what it's extensively used as in Euclidean space geometry. But for coordinate systems, so I have to do some discrepancies here. I've been interchangeably using the words coordinate systems, Euclidean space, and so on and so forth. So if I keep using the word Euclidean space, just know that I'm talking about mechanics or something related to physics. If I say coordinate systems, it's more or less mapping of things. It doesn't have to be physical object or something related to physics or chemistry or whatsoever. So coordinate systems are extensively used in any field of study, be it science, business, art, or whatsoever. Okay, now I really want to give a good mathematical basis of the Cartesian coordinate system. The Cartesian coordinate system is what we use every time. For that, you need to understand. I'll just do some brief things on sets. Um, there are different degrees of densities of numbers. So, um, the first level of density is called the natural numbers. There are some mathematicians have to have the argument if zero is part of the if zero is part of natural numbers. But for the sake of simplicity, let's include zero to be part of um, the natural numbers. So natural numbers are discrete numbers. They start from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we talk about things like, okay, so we talk about things like is addition closed under the natural number set? You say yes, because if you add any two natural numbers, you always get a natural number. You say it's subtraction, sorry, it's a natural set closed on the subtraction. Well, it's no, because you can have two natural numbers. You take the difference between both of them, and you have negative numbers. But natural numbers do not include negative numbers. So you say, okay, what kind of numbers can we extend to so that negative numbers will be included? So we have a different degree of density of numbers. We call them the integers. So they're one step higher than the natural numbers, in which the subtraction algebraic operator works. So okay, so we're satisfied with that. So we start to do things like, okay, if the integers is closed on the subtraction, what about division? Is it closed on the division? They're like, no. Okay, let's get to rational numbers. Rational numbers is a more the numbers, they are more dense than integers. So we start to do things like, okay, what about if we have things like pi, e, root 2? Are those things closed on what I mean by root 2 and so on and so forth? So acertic terms, are they closed on the rational numbers? The answer is no. So okay, let's go with rational numbers. So the highest so far, the most dense real number system, or real number sets, we don't call them system. I don't know if anyone calls them system. I call them set. Real number set are the real numbers. So the real numbers is a set of. So it's a set in which the integers, natural numbers, irrational numbers, and rational numbers are subsets of the real number set. So we have real numbers.